go and pull up my max flow picture. So max flow is a completely different graph problem, but it turns out that, as we'll see this week and probably next Monday, that max flow and min cut are related, so that if you have a max flow solver, you can use that as a way to come up with min cut. Like, finding the min cut directly seems hard, but on the other hand, if we can use a max flow solver to solve min cut, then this sort of, anyway, this sort of thing comes up a lot in computer science, as I'm sure you've seen in other contexts, where one of the key tools of a computer scientist is being able to use a pre-made solution to some related problem and somehow like squint at that solution and go and like tinker with it just a little bit to solve the problem that you really care about or that your customer really needs you to solve. Question. Hunter's question, which I think is related here, is if you were trying to go and find, like, let's say I was interested in finding, okay, if I wanted to disconnect New York and LA, and I had a huge botnet. Botnet is like, I infect a huge number of machines with some virus that gives me control over them, and I'm going to launch a massive denial of service attack on the North American internet. And being the evil person that I am, I want to go and target my denial of service attack at the weakest links, or find the cheapest way to launch a denial of service attack that would break all of the links necessary to disconnect LA and New York. So that would be like a min cut problem, and using the brute force approach would not work there. If I wanted to figure out for a crazy graph like the North American internet, what is the most effective way for a bad person to denial of service particular links to take down California to New York connectivity, if I wanted to do that, I would need a better algorithm. I would need something better than brute force. And in fact, what I would do is I would probably go and use this max flow approach, which I'm going to discuss today. Olympia?
So I have a question. So
sure.
How do you reconcile the issue? Like, we talked about how you can use minimum spanning trees to like lay network cable in the cheapest way possible. So like, how do you reconcile the fact that using a minimum spanning tree to do that and like having the cheapest way to connect to points also makes min cut super easy?
It makes it so. First of all, it makes min cut super easy, and it makes your network incredibly fragile because you end up being like very cuttable. And ultimately, this trade-off between resiliency versus cheapness of creating it, like this problem, I don't have an answer for it, but this trade-off is inherent in like all sorts of transportation and communication infrastructure across the country. So like, I mean, this is also things like, I live up in Manatee County. How many bridges should we have across the Manatee River? Well, if you only have one bridge across the Manatee River and there's an accident there, then you've disconnected like Upper Manatee with Sarasota. On the other hand, these bridges are like super expensive. And so if you want to be really resilient so that high traffic or like, denial of service, I think in the bridge world, like denial of service is probably just tourists from up north. Denial, so if you have like traffic or you were worried about like accidents going and clogging up a bridge, then you can build parallel infrastructure for robustness, but this goes and increases the cost. And maybe there's an interesting problem, which I think we're not going to solve here. But there might be an interesting problem of looking at a graph and finding like what is the cheapest way to span the graph, the minimum span of the graph, subject to the constraint that the min cut is at least 3 or the min cut is at least whatever. Because yeah, Olympia is absolutely right that if you use a minimal spanning tree to go and lay your cable, then your network ends up being fragile and somewhere you're going to have a really cheap cut. Now, last comment on this question, because anyway, I think these trade-offs are really interesting, is at a place like New College campus, it could be the case that at a place like New College campus or some similar location, that cost is really the driving factor. That if we end up with a temporary disconnection between the student side of campus and the academic side of campus, maybe like that's a risk we're willing to take, and we're happy to have the network be fragile because cost is really the issue that New College cares about the most, and building redundant connectivity across 41 might be really expensive. And so like it's a trade-off which is going to depend on the circumstances, the resources available. This is like a cost-benefit analysis of what's the risk of being disconnected, how bad is that, versus like how expensive is it to actually fix the problem. Okay, so pop back very quickly. Wonderful. I like that question. So max flow is max flow is a problem where we are trying to get something, and I'll discuss something in a minute, from, so we'll do A again. No. No. Text to B. Okay, so max flow, we are trying to, this is a related problem where we are trying to get something from A to B. And the something that we're trying to get, I mean, this could be, again, a logistics network where we're trying to ship widgets from A to B, and there's a number of, what do I want to say? There's a number of intermediate stopover points. Maybe these circles are warehouses, and these are like shipping lanes or trucking lanes that I can use to go and move stuff like from A to this warehouse, and then to this warehouse, and then to this warehouse, and then to this warehouse. And so the key with max flow is that, and can I grab a different color here? So the numbers for max flow are capacity. No. Okay. So these numbers represent the capacity. I mean, you can also think of this in terms of like an oil pipeline or a public water pipeline. I'm trying to pump water from A to B, and I have a bunch of pipes that I can move the water through, and all of the numbers on these pipes are the capacity for how much water I can move through here every minute. And I want to send water from the source all the way over to the sink. So let me check quickly. Okay. So one way, for example, that I could go and send water is I could go and send like 2 units of water here, and I could go and then send that water here, and then I could split. So this is like 1, 1, 1, 1. These pictures are not great. This is another 2. So this flow, I send 2 units along this edge, 2 units along this edge. Then now there's nowhere that I can send those. Once they get to this switching station, there is no place that I can send those 2 units. Because I've only got pipes of size 1. So therefore, I could go and ship 1 unit up here, 1 unit down there, 1, 1. So then I've got like 1 unit is taking the bottom path, 1 unit is taking the top path, and in total I have pushed 2 units of water from A to B. So we call this like this assignment of goods to edges, or like water to pipes. This assignment of how much water do I push through each pipe is the how much water do I push through each pipe is we call that a flow. So this is one particular flow, and this is a flow of 2 units of water from A to B. And again, sorry, this could it could be water going through pipes. It could be like boxes on trucks. It could be people on airplanes. Maybe you have some airplanes that can, one person's probably silly, but you have like maybe a 40-person airplane and a tiny 10-person airplane. And then this flight is like a 30-person airplane. And so we want to get these 2 passengers from A to B. So we hop 1, 2. Here we're going to have to split those 2 passengers up along 2 different routes because we have limited capacity. So let me check for questions. I'm going to pause for a moment to ask for questions. So
I was wondering, so is the goal in this to do some kind of like cheapest or most efficient flow, or is that different?
Yeah, so there's so there are a lot of different flows in this graph. Like in addition to this flow, another flow is I could just send one thing from here to here to here to here. I could do just like push things along the bottom, and I could push like 1 person or 1 unit of water along the bottom. So there's a bunch of different flows. And I think Courtney's question is like, well, if there's a bunch of different flows, which one do we like? And generally, what we're looking for when we think about flow is, I'm going to erase these quickly. So generally, when we're thinking about flow, so this is
So the objective of Maxwell is to avoid the bottlenecks then?
Yeah. So and this is why this is related to min cut, which again is something that we will talk more about on Monday. But this is related to min cut because if we want to push as much so if we want to push as much flow as possible, then we're gonna need to avoid as much as possible bottlenecks. Those bottlenecks will cause us problems if we're trying to push as much flow as possible. And min flow is a problem that's all about bottlenecks. So like philosophically, maybe there's like kind of a connection here. And also, let me just demonstrate for you. So I think the previous flow that I showed you was a flow that was 2 units of flow. So I could do a more complicated flow, which is like I could send so like 2 up and 2 down. And then here I've got 2 units of flow. I'll send 1 here and 1 here. And then here I'm going to split these, and we'll have like 1 here and 1 here. And then now I've got 2 units of flow, 2 items, 2 passengers coming into this place. 1 from the top, 1 from the bottom. So I can push those out like 1 and, oops, let's, 1 and 1. And similarly here, I can push a unit of flow here. So now I've got 2 units of flow coming in here. So that's a 2. And here I have 1 unit coming in. I need to have 1 unit going out. 2 units come in here. So this is a way that I can go and push 2 units of flow through my pipe network or my transportation network. So the, yeah, does this is a complicated flow. Does this make sense? I'm gonna check questions. Yeah, so to Eric's question, yeah, so for Eric's question, there's no explicit notion of time here. So we can't, again, if you think about like water rushing through pipes, maybe water rushing through pipes is the best analogy, and I'm sending like 2 gallons per second through a pipe, and here's like 1 gallon per second. And if I'm pushing 1 gallon per second in here and 1 gallon per second is coming from the other direction, this like junction has 2 gallons per second coming in. So I need to be pushing out 2 gallons per second. The amount of stuff that is incoming needs to be equal to the amount of stuff that is outgoing. So I don't, I can't like store a whole bunch of water at some intermediate junction and wait for later. Although that's like, it's an interesting variation of the problem, but in the pure form of max flow, we are only interested in pushing the, pushing water like every second through the network so that however much water goes in needs to be the same amount that's coming out. Next question. Yeah, and so this problem doesn't make sense with negative capacity. It doesn't make sense to talk about a negative capacity for flow. So yeah, I think that we're going to assume that all of the capacities are positive. Any other questions? I'll answer Courtney first and then Hunter. So Courtney's question is, what does a max flow problem look like? And what a max flow problem looks like is, given this network of pipes, among all the different ways that I can push water through this system, what is the one that gets the most water per second from A to B? Yeah, so what the optimization problem that I'm trying to solve here is to figure out what is the best flow? What's the best way to send my water through the system so that I get the most water going from A to B?
But wouldn't that just be like using all of the edges? Like using all the pipes would get you the most flow?
So yes, but the so there's a question of like, how do I figure out what the max flow is? And so your intuition is right that max flow is definitely a problem that we can solve. And there is a good solution to the max flow problem. But there still are some choices to be made here, in the sense that, like, let's say that I flow 2 units from along. Let me go, and I'm actually going to go erase all of this for a second. So if I go and flow, so I'm going to go and start out, say, hey, let me go and flow like 2 units down here, and then I'll also, like, why don't I start by trying to like flow 4 units up there? At this point, I have 2 units coming in, and I have capacity. I could send all of those 2 units up here, or I could go and send like one of the units down here. So like I've only got 2 units of flow coming in here, and so I can't use all of the capacity that I have coming out of this junction. So then the difficult choice that I need to make is, should I go and flow like both of those 2 units up, or should I go and flow down? And like split, should I split here, or do I not want to split here? Because I've only got a limited amount of flow coming in to work with. And in order to know that, like, the only way to know that I want to split here instead of like sending both of them up is because of other things that I can see in the network. So it isn't obvious when you get to a junction, if you have more flow coming in than you can have going out. Should you split or should you not split is like the tricky question that needs to be solved in order to get the max flow. So then Hunter's question is, so if you want to send out for water and you have a route with capacity for, yeah, so there's Hunter's question is, I think, getting, oh, sorry, this is, did I just pop my Steam button, which is not necessary? So, close that. So I think what Hunter was getting at was, if I understood his question correctly, was the same issue of like, do I send, if I'm trying to send for flow through this network, like, should I split it, or should I like concentrate it along one path, or should I split it along several paths? And the answer is that it depends on the graph. And I think I'd like you to play a little bit in the homework assignment. I think I asked you to play around a bit with some example paths for max flow, but it's not always obvious without looking more broadly at the network to figure out whether you should split or not split. Let me check back with Eric. No, so Eric, number of edges isn't a concern. So you could imagine variations on this problem, where maybe a variant of this problem is that it takes a while is to consider the time propagation of different paths. And for the pure version of max flow, for the pure version of max flow, everything is instantaneous and we're not considering travel times, but like considering path length and preferring short paths is that's definitely a consideration for some practical applications of this. But for the pure theory problem, everything moves like instantaneously, and we're not going to be concerned about propagation delays. Okay. So any more questions on like, what is the max flow problem? What are we trying to do here?
Yeah, I just wanted to clarify. So you were saying that, like, for example, if you're pushing 2 units through like where the red line is, you have to like choose whether like what you're going to do with it, and you're like, you can split it or you cannot split it. But I don't understand like what bad would happen. Like, what would be a bad situation for, like, if you choose to split it and you weren't supposed to, that was a bad choice. Like, what does that mean happens versus like if you didn't split it and that's good? Like, what's does that make sense? I don't really get the objective.
Okay.
Versus bad.
So let's say here, let's say that this edge, or actually maybe I just go and like white all of this out. Let's say that this edge didn't exist and this is a dead end. So in this case, if we're sending 2 flow along here, and also I'm going to up the capacity here slightly. So, I will erase those later. So if like on the upper, so here you worry about like running into a dead end or a blockade where like you have more stuff going into a node than that node can handle, and that's wasted. So if here I were to go and split this flow like 1-1, if I were to split this 1-1, this one gets here, finds that there's like no capacity for output, and then like this water or this good or whatever item I'm moving through my network, this is just wasted because it never gets to the sink. So does that answer your question, Courtney?
Yeah, kind of. So like you want to avoid dead ends?
You want to avoid dead ends, and like more generally, you want to avoid, like in this case, splitting is bad because there's a dead end. On the other hand, if I go back to my original graph, in this case, if I go and like send this up here, and here I'm going to go and send like 4, 1, 3. So here I've now got 5 units of flow coming in, but only 2 can go out. So here I've like wasted a unit of flow, which could have gone along the bottom path, but it was a mistake to go and send it up here to the middle. Okay. So because in this case, I've got a bottleneck coming out of the middle, and so I don't want to send too much stuff to the middle because the bottleneck is the middle. On the other hand, if there was a dead end along the bottom, then I might want to send up to the middle. So it depends on the graph.
Okay, so in those bottleneck situations, like the ones that don't get through, for in this case, like the 3 that don't get through the center intersection, they just like, they're lost.
They're lost. I only get paid. I only get paid for the units of flow that make it to B.
So you want to avoid like dead ends and bottlenecks and anything. You don't want to send more into a node than can go out the other side of the edge.
Yes, that's exactly right.
Okay,
that's exactly right. So, okay. So I'm just going to check questions.